All right, let's try that again. Good morning. Well, I'm reminded today that no one's in class logged in, and I am reminded of a story I read or heard once about Isaac Newton. Apparently, he was somewhat of a boring lecturer, at least before he became famous. 2 or 3 years before he published his Principia, he was already a professor, I think, at Cambridge. Anyway, no one came to his lectures. And what's interesting about that is that he famously would always come to class to an empty hall, open his notes and lecture for however long he was required to lecture as if students were there. And he did this apparently for years. So in the spirit of Isaac Newton, let's begin. And I apologize, even though no one's here, for being late. Last week, somehow I got my signal crossed and taught 30 minutes over time. There were a few people in class at the time. This time I started late, so I think I'm just having a low fall start. I taught summer school and we got a little burnt out at the beginning of the semester, or at least not burnt out, but just maybe I needed a little bit more break or something. But the nice thing about this new era that we're in is that you already have all the lectures. So you can always work ahead. Well, we had introduced Coulomb's law last week, and I think I took the time to. We just had one day last week, and I took the time to review vector analysis, where we looked at the force on the charge for a system of discrete charges. But there is a difference between a force and a field. So we need to distinguish between, how we use those words. A lot of times last semester, for example, we talked about gravitational acceleration versus gravitational force. And we didn't explicitly describe the concept of a field last semester because, well, generally that's not really done. But the acceleration, you can think of it as more than just a kinematic quantity associated with a specific object, for example, as an object experiences free fall motion. That's just one perspective. And remember, perspective is one of the themes of the course. Another perspective is that since all objects have we assume that acceleration is constant near the surface of the Earth, you can think of that acceleration as being something associated with the atmosphere, the environment. It's just a different perspective of thinking about it. I actually go into this when I do gravity. But at any rate, the acceleration can be thought of as a field, and the force that an object experiences, the gravitational force, as can be thought of as coming from that field as opposed to coming from the Earth. So in the same way, two charges can have a force on them. Newton's third law, electrostatic force, for example, gravitational force, same thing. But let's switch back to gravitational force at this, electrostatic force at this point. But we can also, and there should have been a section that talked about this a little bit, that talked about field lines. I guess this is the section where you talk about it. Associated with the charge. So let's say that we have a positive charge. So this section is going to be called the electric field. Now, as I was saying before, and let's go with a dipole. A dipole is a specific type of charge distribution where there are two charges of opposite polarity. So if we have a dipole, a positive charge and a negative charge, let's say, well, we know, just like we talked about last week, we're going to have mutual forces of these charges on one another. And because of the nature of charge, as we discussed, these forces will be attractive. So you will have a force of, let's call this, so a force on the negative charge acting through the center of the charge toward the positive charge. And that force will be due to the positive charge. So we can call that, I need to number them. Let me go ahead and do that. The terminology that can get confusing, I think, if you know. So F, this is the force of charge 1 on charge 2. And equal and opposite to that is a force charge 2 on charge 1. It goes to the center. Of 2 on 1. So those forces might look something like that. So sure, we did that. But if you look at each individual charge itself, it turns out positive charges have field lines that extend radially away from, well, I don't want to introduce this. Yeah, so the Coulomb force was established as, so F, we said F12 equals the negative of F21. We define this as a Coulomb force, the magnitude of F, called equal to F. And that Coulomb force we said was equal to K sub B for these two forces, Q1, Q2 over R squared, R hat. Well, I guess I should just start by saying Michael Faraday defined the field as, something that can exist around the charge that sometimes you don't know what a charge distribution is. That's the point. You don't know what the charge distribution looks like, but you have other charges in the vicinity of those the environment affected by this distribution of charge. So what Michael Faraday proposed is that basically, in order for these charges to force upon one another, there must be something that they're doing or putting out in the atmosphere that the other charges can detect. And so he defined that thing as a field, and he defined it in terms of the force. So what he said is that he postulated that no force, no charge can force upon itself. So therefore, the field must not be affected, that it's putting out can affect other charges, but it must not be affecting itself. You can say the same thing about gravity, right? We don't when you're near someone else, a peer or something, you do apply gravitational attraction to that person. However, you don't apply gravitational attraction to yourself, right? So, yeah, basically that was the postulate, and so he decided that whatever, since as we determined last week, a charge can contribute to the mutual force between two charges, but it can't directly put a force on itself. So therefore, if you put those two kind of concepts qualitatively together, and since we have a quantitative uh, definition of the force between the two charges that we can determine are equal, or the equal magnitude on each charge, then the field of a particular charge must be proportional to that force, but can't contribute to it itself. So then in this particular case, if I want to know the field associated with charge 2, that field, which he used the symbol E, must be proportional to that. And so proportional to, E must be proportional to F. And we must divide out the charge associated with the specific field. So say the electric field associated with charge 2 must be equal to the force between the two charges divided by charge 2. So therefore, if we put those two things together, in fact, this is a definition, so let me just say that, then we can say just easily derive it, right? You take equation um, three and substitute into equation 2. So if I solve for equation 3, so this is the definition of the electric field. It's defined as the electric force, electrostatic force divided by the charge. So let's just make that in general. Box that in. And so then I can get another equation for the electric field in terms of the charge by equating, well, solving equation 3 for F. F then is equal to Q times E. So if I then equate equations 2 and 4, what I have is that Q, make it Q2, okay, Q2 times E 2 is equal to K sub B Q1 Q2 divided by R squared. So the Q's Q2 cancels, and the electric field associated with charge 2, that is, the electric field in the vicinity of charge 2, is going to be equal to K sub B um, sorry. That is, I misdefined it. It's QE1. So you divide out, oh God, good morning. The charge can't contribute to the field that it's, right. So it's the other way around. So this should be E1. E1 Q2 is the force on the charge divided by the charge. So the force on Q2 is F21, right? That's right. So F21, yeah. Yeah, I set it up wrong. So it's E1 because charge 2, as I said, you can think about the force on charge 2, for example, coming from charge 1 or coming from the field that charge 1 sets up, right? My bad. So this should have been E1, and so I need to divide that by Q2. That's right. Right. So either the force on Q2 is coming from charge 1 or it's coming from the field associated with charge 1. So it's the external field that the charge 2 feels, and therefore the force that it's feel, but the charge we're discussing is charge 2. So my bad. Right. And so F21 is equal to F2, F12, so that doesn't matter. I'll just take the F. That's equal to Q2 over E1. And this is E1. So dividing by Q2, yeah, so that's right. So in the end, we get the electric field associated with charge 1, K sub B, is equal to K sub B times Q1 over R squared, R hat. Similarly, the force on charge 1 is either equal to, you can think of it as coming from charge 2 or coming from the field associated with charge 2. And a same derivation would lead to the fact that the electric field associated with charge 2 is equal to K sub B Q2 over R squared, R hat. And remember, R squared is the distance between the two charges. So in general, we can write a equation for the field that mimics the equations that we wrote for force for all the various charge distributions. That is, in E is equal to K sub B, Q. So oftentimes it's written as a Q naught, but I'll just write Q over R squared, R hat. So that's the field associated with one particular charge. If you had a series of charges in an area and you wanted to determine the electric field at a point in space associated with those, various charge distributions, with that charge distribution, i.e. the various charges. So let's say we've got a series of charges here, Q1, 2, 3, 4, and we have a point in space, point P. Now, you don't necessarily have to have this. The nice thing about a field is that you don't necessarily have to have a charge at that point. So this is just a point in space. Point P is an arbitrary point in space. With no charge necessarily at that point. So there will be a field at the point P associated with the various fields of the various charges. Guess that's one thing I should have done before describing this. Visually show you what the field looks like for these two charges. So the magnitude of the field, let me go ahead and put that back in, is going to be equal to these formulas. So if I want to know the direction, if I look at a positive charge, the field associated with the positive charge basically points radially away from the center of the charge. So for a positive charge, the field lines radially means it starts at the center and just points out directly from the center, making perpendicular line with the tangent to the point where it crosses the charge distribution. So for a circular charge distribution, which we kind of assume, I mean, it's a point particle, but if we assume a circular charge distribution, blow it up a little bit, radially means that if you start at the center and just move directly out in either direction, that will be the direction of the field. Now, technically, it's a point charge. So I'm just going to draw a point. I'm going to make it a point, and we'll talk about the kind of the distribution whenever we have some volume associated with the source. But radially outward looks like this. So we establish a set of what we call field lines. I'll write out some properties associated with field lines momentarily. But this is a positive charge, the field lines associated with the positive charge are doing this. So it's positive. And a negative charge, we have a very similar charge distribution, except that the direction of the fields are different. They're in the opposite direction, so they point toward the negative, inwardly toward the center, radially inward toward the center of the negative charge distribution. So those field lines would look something like this. Different color. So I'm going to come back to this point in a second. So what we say is that we call the charges poles, and we say that these charges are the sources of the fields associated with these charges. So positive and negative charges are poles. We call them, when we think of them separately, we call them monopoles. Mono, Latin means one. And if we put two together, as we've done in this case, we call that a dipole. Well, dipole is a specific type of charge distribution. It's one in which you have opposite polarity, but the charges have the same magnitude. And what we'll see is that it creates, when we put them together, the field lines have to connect and they create a field line pattern. But individual monopoles, in electrostatic, we say that the charges are the sources of the fields, and we refer to them as monopole. Monopole. Positive and negative charges are the source of the electrostatic field. Source says of the electrostatic field. And this field is indicated by field lines. The E field, that is. By field lines or a field line distribution. Let me take this. As I said, I'm going to come back to this point. So we can say that charges are considered the sources of the electrostatic field. Oh, I said that, right? Now, yeah, I guess it's an off day today, folks. Hello, Evil Gang. How are you today?
Good, Professor. Good morning.
Good morning. Good morning. Good morning. Have a bit of a slow start today. Getting some feedback. I'm not sure what's happening yet, but anyway, good to see you. I hope you had a good weekend. And yeah, so we're moving along with this lecture on the electrostatic fields. I've got a kind of a bit of a lot to do today. But
Yes, sir.
yeah, we looked at the force on charges, charge distribution, calculated that. Now I'm defining something called a field in association with that. All right, so we can represent the electrostatic field as field lines, and they have specific properties that we're going over right now. So field lines are defined by this equation here in general, and actually it's defined by this equation, equation 3, and equation 8 is kind of a practical application of it. Basically, equation 8 shows you how to calculate the electric field for a particular charge distribution. It was defined by Michael Faraday in the 1820s-ish, something like that. And I've been using the term electrostatic. That means that here we can kind of look at it like this field, as long as the charge is not moving, then this field line, these field lines, as this equation states, its field intensity gets stronger as you get close to the source, close to the charge. And that's indicated by the line density of the field lines. It's one way to represent it. Now, to be fair, fields, if you could see them, they wouldn't look like arrows around the charge, right? If anything, it might look like a cloud, maybe like fog or something, and it gets more dense as you get closer to the charge distribution. Even that isn't fully correct, really, because it doesn't give you an indication of direction. But this is just supposed to represent, obviously, an analogy for what's actually what we're trying to define. And also, this is a two-dimensional representation. If you could, a more adequate representation in 3 dimensions, you know, it would look something like a porcupine, where the field lines would be coming out in all directions proportionally. But as you get closer, you can tell that the field is getting stronger because, as I said, the line density is increasing, meaning if I were to take a radius, say here, and I calculate, so that's going to be at some position R1, let's say. And let's say I take another radius from the center that's here, and I call that R2. Line density is defined as basically the number of lines per unit area in this case, or if I were thinking of it in 3 dimensions, it would be the number of lines, field lines per unit volume. Well, I've only got 8 field lines, right? Line density is defined as lines per unit area in the case of 2-dimensional case, or lines, number of lines number of lines per unit volume in the three-dimensional case. Let's work at 2 dimensions. So for R1, the line density would be 8 divided by the area associated with radius 1. And radius 1 is pi R1 1 squared. And the I don't have a symbol for line density yet. You just say I don't know. Yeah, I'll just say 4 R1 and do the rest. That doesn't. So for R1, that would be the line density. For the radius 2, the shorter radius, it's still going to be 8 lines going through it, right? But the radius in that case would be pi times R2 squared. But if R1 is greater than R2, then I'm dividing the number 8 by a larger number, which means that, and I should have some, let me just give me a symbol for that. Actually, there is no symbol as well. So I'm just going to say, come up with some. Yeah. I'm just going to say, I'm going to abbreviate it LD. I'm going to say line density for radius 1. I'm going to call this line density for radius 2. So if radius 1 is greater than radius 2, then we can say that the line density for radius 1 is less than the line density for radius 2. So we can say that line density is proportional to field strength. Line density is proportional to field strength. Yeah. The positive and negative charges are sources of the electrostatic field. We refer to them as monopole. I didn't write that up. I said if I didn't write it up, then we went into, it was a different point. Line density is defined here. And line density proportional to field strength. So it's proportional to E. One way that you say this mathematically is that, that the line density, here. Say that the line density proportional to E, magnitude of E. So this is a mathematical way of stating this point. Line density proportional to field strength E, magnitude. I hope that doesn't look too messy. Somewhat ordered. Yeah, okay. So point charges are called monopoles. That's kind of a deduction from this. Monopoles or point charges are considered monopoles because they are considered the sources of the
What did
field
you
line.
say? Which charges?
Any charge.
You say you said something like some charges are called monopoles or something.
Yeah, any charge.
Oh, any charge?
Yes.
Okay. All right.
Yeah. So yeah, any charge, because you can't, I think you came into the lecture kind of midstream of that point, but that's what I'm saying here. Positive and negative charges are the sources of the electrostatic field. I've illustrated that with these original diagrams. And these lines represent field lines. You see how these field lines for the positive charge are radiating out radially away from the charge, point charge. And here for the negative charge, the lines are radiating radially, that means toward the center, but in toward that charge. So whenever you have a charge in a region, those charges represent the sources of the fields around it. Does that make sense?
Yes, sir.
Yeah, so that's what I'm saying. I'm reiterating that point. And we refer to them as monopole. They are the poles, P-O-L-E-S, associated with those.
That's what I was trying to hear. Monopoles.
Monopoles, that's right. So monopoles, single charge distributions are called monopoles. Single charges, mono, M-O-N-O-P-O-L. Yeah. All right. Yes.
Yes, I heard.
Good. A dipole, we got to be a little bit careful here. A dipole is a specific type of charge distribution with obviously two charges, but it's not just two arbitrary charges. The two charges have to have the same magnitude. So a dipole specifically looks like the following. The charge distribution will look like the following. I have a positive charge, you just do it like this. So a positive charge here, a negative charge here. The fields interact with one another. And so what we see is that because of the nature of the field lines, what I said here, field lines radiate inward toward a negative charge and outward away from a positive charge. If you take one line coming from the positive charge here, it's going to move radially away from the positive charge toward the negative charge. So that satisfies the two criteria. In other words, here, if I take this line here, I can just connect these two, kind of like this, right? Guess I could have just done it here. And then this field is going away, this field line here, let's just do it over here. This field line is going away, that's going to, and at some point, they might connect. Same thing here. Guys doing that. I think this was coming in. So what you ultimately get, and I can put more lines in. And the thing about a dipole is that since the magnitude of the charge is the same, that means in any point in space, the number of lines or the line density is the field strength is, well, not necessarily the same, but it's mutual. So in other words, when I represent the field as field lines, for a dipole, I would always have the same number of fields coming out of the positive charge as, excuse me, as going into the negative charge. Yeah, you see it over here. So a more filled out distribution for a dipole would look something like that. Always with the same number of charges going out as coming in. So that's a dipole distribution. If the negative charge were larger in magnitude, then not all the lines would connect. I would have to have more lines coming out of the negative charge or going into the negative charge as coming out of the positive charge. And if you look in the chapter in your book where they discuss this, they should have various charge distributions. Now, just because you have a positive and negative charge, if the charges are not of the same magnitude, then it's not referred to as a dipole. You can still have that, but it's just not called a dipole. It would just be two charges of different magnitude, opposite polarity in close proximity, and you would draw the field line distribution accordingly, but it would not be symmetric. And there's that word again. This is considered a symmetric field distribution because you have the same number of field lines exiting the positive charge as entering the negative charge. That's what a dipole is. So charges of opposite polarity in close proximity and equal charges of opposite polarity and equal magnitude in close proximity. That's what a dipole is. Yeah, right, dipole. So, still discussing the properties of fields, of electrostatic field. A couple other things I want to say about this equation, this definition of E field. So yeah, I'll go back to the point that I was making about electric field being just associated with a point in space. The chart in this equation, basically, you know how I told you that, let's say, if you look at this, so we had defined R being the value of, when we were thinking about Coulomb's law, it was the distance between two charges. But because this equation is set up and there's only one charge, electric field is only proportional. Basically, E is proportional to Q and it's inversely proportional to R squared, whereas the Coulomb force was proportional to the product of two charges, Q1 times Q2, and inversely proportional to the square of the distance between an inverse square. So we see that the electric field is still an inverse square law, but it's proportional only to one charge. Now, in the derivation of this formula, I kind of had a dyslexic moment and switched the charges in the derivation. So hopefully I could don't want you to be confused about this, so I'm going to kind of drop that analytical point of view and just talk to you with common sense. Now let's go back to thinking about force. Because I've been describing or making an analogy between the universal law of gravity, I started last week doing that in Coulomb's law. I'm going to go back to something that's a bit more intuitive to you, talking about gravity, and to guide your intuition. If you have two objects, let's say two people, they're in close proximity, I think we know by now that they would apply a very small gravitational force on one another, small compared to the weight of the object, of the individual. But if I were to think of myself, and let's just take me in this classroom. Let's say me and this object right here. So this pen and I, there's a mutual gravitational attraction between us. However, if I were to think about, and so if I were to calculate that force, it would be equal. Why? Because the gravitational force is proportional to the product of the mass of the pen and my mass. But what we're trying to do is think about the concept of field independent of the source. That's the purpose of it, of defining a field. In other words, if I were to remove this pin, so I'm applying a force on the pin, right? Due to my accumulated mass of my body. So there's clearly a gravitational force on the pin due to me. But if I remove the pin, is there a force at the point where the pin once existed? And the answer is obviously no, because there's nothing there to force upon. But if you bring the pin back, then the force appears again. Now, what if somehow you could put me in a box, right? You didn't know that, some sort of invisible box, and you couldn't really, even though I am the source of the force on the pin, someone external to that the pin itself, let's say, wouldn't necessarily be able to see that because they only see the box. And I don't know, maybe it's a box that doesn't have mass, so it's not a gravitational field, and it's somehow, it's just invisible. So this makes me invisible, right? You can't see me. You know there's something inside. I guess what I'm trying to illustrate is that you would then be able to, even though there's a force on the pin, you could associate the force with the field in the area around the box, the field in the vicinity of the point where the pin is. And even though you didn't know what the source looked like, you know there must be some source within the box because there's a force on the box. So what I'm trying to illustrate is that whether or not there's a pin there or not, there will still be something in the region, a field that could give force, that could cause a force if something is there to take advantage of it or be affected by it. It's kind of one of those things, reminds me of that question that I first heard when I was a kid. You know, if a tree falls in the forest, does it make a sound if no one is there? Well, the answer is yes, it does, but there's no one there to take advantage or to hear that force. I can make an analogy between this situation. If you're in the vicinity of some region of space and it doesn't look like something is around, like if I'm way out in the middle of, like, here, I don't know, like, I guess you still would be able to see a source. Let's say something like a black hole or something. I don't know. You can't see a black hole, right? But if you're in the vicinity of that black hole, are you still affected by the gravitational attraction? And the answer is yes, even though you can't see it, yes, you are, right? Even now, I mean, technically speaking, the nature of this equation is that it doesn't get to be zero until infinity. We talked about that last week with the Coulomb's law. Because you're dividing by r, the farther you get away from that field, it decreases, but it's never zero until you're at infinity, right? Because only infinity, the inverse of infinity is zero. Similarly, as you move into the charge or to a point, or in this case, to a charge, we say that as you move toward the center of a charge distribution for a point charge, for example, the field is not defined in the center. And I guess that's just the point I'm trying to make, which is that even though a charge is the source of the field, one, the field is not defined at the center, and two, if you're at a point in space, the field is determined by basically a charge cannot contribute to the field in a region of space. I don't know why I'm struggling to say this morning to illustrate this point. Just using the wording. Okay. Yeah, in my notes, I guess I said it differently. I illustrated this or explained the point differently. What I did is introduce the concept of a test charge and use that to make the point that I'm making. So let me do that. Let me do that because otherwise I don't know, I'm not having a very coherent morning. Test charge, the concept of a test charge. A test charge, I think I kind of mentioned this the other day, but let's reiterate it. A test charge is something that's a charge that's positive and very, very small. So it doesn't really change the field in an area, the magnitude or the field strength. That is to say, let's say that I have a large charge Q in a vicinity in space, and let's make it a negative charge. So negative Q. Well, we know the field will look something like this. Right to the end, okay. And let's say that I wanted to test the region around that charge to see if there's a field there. Well, one thing I could do is use a test charge to do so. So let's do this. Let's have a thought experiment where we do that and illustrate how a test charge is used. So I take a test charge, which is a very small positive charge, and I just put it here. And what I will find is that there will be an attractive force on that charge. So that's telling me that if there's an attractive force on it, then if I divide the force by the magnitude of the test charge, let's say that the test charge is Q naught. So again, if I divide the test charge by the magnitude, divide the force on the test charge by the magnitude of the test charge, it's going to give me the value of the field E at point P, at this point. But that field will not be, there will be no contribution to the field by Q naught because I'm dividing it out. So even though there is a field in that area, a charge cannot contribute to the value of the field at the point where it exists. I guess that's the language I was struggling for. In the definition of the electric field, a charge cannot contribute to the value of the field at a point in space where it exists, where that charge is. And mathematically, that's justified because in the definition of E, base of E Q over R squared, if a charge Q naught contributed to the field at that point, well, R represents the distance that you are away from the charge. So I would be at position 0 away from the charge if I'm talking about the actual point where the charge is. So here I would get, you know, a delta function. I would get it would blow up. So, and you know, we say that the reason to avoid that in math, we say that division by 0 is undefined because you basically get infinity. You would get an infinite field if you allowed that. So at a point in space, so two things come from this. Whereas for a force, you need to have a charge in some position if what's the language that technically a because of the Newton's third law and the nature of the Coulomb force, similar to the gravitational force, that force is proportional to the product of a charge between the product of the charges between two charges. Then you can say that an object contributes to the value of the force on itself. You can say that. But so therefore, obviously, the mutual force on an object is, it gives a contribution to the force in the position where it is. But in terms of the electric field, you cannot say that a charge contributes to the value. That a charge contributes to the value of the field at the point where it exists. Testing, testing. Yeah.
Yeah,
Go ahead.
no, I said I can hear.
Okay, good. Yeah. So that's a major point. And one difference between force and field.
Professor, why am I alone in the class? But there are students in the Discord.
What's that now?
No, I was just saying, well, sorry for asking. I'm just saying, why
That's
am
all
I
right.
alone in the class though? There are other students in the Discord.
Other students in the what? This what?
It's an app that we communicate for this class.
Or discourse.
Discord.
There are no students in the class right now because they just didn't come to class today.
Okay. All right.
Yeah, I guess technically, yeah, I don't know. People are they look at the videos, I guess, and didn't come to class. I assume that's why.
Okay, I understand.
There's maybe 30 some students in the class. Even the other day, when you were here the other day, we only had 3 or 4 students in the class because most people, for whatever reason, didn't show up.
Okay, I understand. I was surprised that at that app where we help each other with the homework, there were students there.
How many students per? So there's an app where you do that within the Canvas.
I got responded by like 3 of them, but they communicate.
What is the app that you're referring to?
Discord. Let me see. Let me double check.
Oh, I'm not familiar with that. I guess that's why I didn't know what you were talking about.
It's where the student use it a lot just to
Show
meet
me.
up.
Can you share your screen and show me? Like I'm not familiar with that app.
Discord
Is it?
is D-S, I mean, sorry, D-I-S-C-O-D, I mean, R-D. I'll write it in the chat. Let me.
I understand the word. I'm asking you, what is it? Is it an app or is it something within the Canvas shell?
It's an app. It's an app.
I see.
I mean, all the classes that I've been taking, the students always use that app to communicate, to help each other with the homework.
Really? That's good. Yeah, I'm just unfamiliar with that app, but that's great. I thought there was something within Canvas that allowed for that, but I'm sure there's other software that are probably better, and maybe that's what that is. So, yeah, Discord. Instant message platform. Okay, cool. All right, well, that's good. Okay. Yeah. So I guess that wasn't a very smooth introduction to electric field, but that's it. That's my introduction to electric field. Uh, yeah. So various kind of properties, electric field, a charge can contribute to the field at the point where it exists. Electric field is proportional to the charge setting up to. So the language that I use, going back to this charge and point charge distribution, uh, what you can talk about the field at any particular point in space around that charge, but you can't really talk about force like that, right? You have to have something to force upon. So you have to have a minimum of two charges for there to exist an electric force and on either of those charges. But you can just have one charge, and everywhere in the vicinity around that charge, there will be an electric field, whether there's a test charge there to be affected by that field or not. So that's of the probably one of the most fundamental differences between force and field. So even though electric field is defined, as we said earlier, in terms of force, it doesn't. It's not. It's definitely something that's very different than force. And in fact, what we see is that when we combine Coulomb's law and the definition of field, we then see that the electric field is actually really equal to all of the system of charges setting up that field. So I'm going back to that earlier point I was about to make. Well, we could do it like this. What I'm saying is that going to this point here, if I come over here and take the point charge away, at some arbitrary point, a distance r away from that charge, there will still be a field at that point, even if there's no charge there to take advantage or be forced upon by it. So call this distance r. And we oftentimes we call points out in space field points. And by convention, oftentimes people use the symbol P, and I do a lot, to represent just some arbitrary point in space. It's not a charge, it's just a point. Point in space, referred to as a field point, a point in the field surrounding some region or some physical phenomena that you're discussing. So there is an electric field at that point, whether there's a charge there or not. So the field then exists in the space around a charge distribution, whether a charge is there or not. Can exist in the space around a charge or a charge distribution. Whether other charges are there or not, or A field can exist in the space around a charge or a charge distribution, whether a charge is at that point or not. The field can exist at a point in space. Let's make it specific to a point. A field can exist at a point in space around a charge or a charge distribution, whether a charge is at that point or not. A charge is at that. Whether a charge is at that point or not. And again, as I said, if a charge is at that point, the charge at that point does not contribute to the field at that point. Only the charges setting up the field, the original charges that we were discussing in this sentence. So that leads to that distribution point I was making earlier. So say that you have various charges in the vicinity, and they can be positive and negative, positive, negative, positive, negative, I don't know, whatever. But over here, we've got a field point. In fact, let's make this a little better, a little more illustrating. That might be confusing. I don't want you to confuse the field point with the charges. So let's say that we have a couple negative charges. So Q1, Q3, then maybe a couple positive charges, 4 and 2. And then we have some field point over here, like so. Well, we can do something similar to what we did with the forces, right? What is this is just a field point, arbitrary field point with no charge at that point. What is the field at point P due to this distribution of charges? Well, qualitatively, you can use the concept of a test charge to determine the direction of the field of the individual charges. In other words, a test charge is always positive and like charges attract. So if I had a test charge at that point, I would have a field line that's pointing directly toward charge 3, because charge 3 is negative and it would be an attractive force. So the field then at that point would be pointing toward charge 2 or charge 3. That's one way to think about it, but I like a different perspective. I think of the charge itself. That is, I know that if I were to see the field lines associated with that charge, they would all have to be pointing radially in toward that charge. So I don't use a test charge concept to figure out the direction of the field. That's probably what your book is going to teach you, the test charge concept, but I don't like that, because I just visualize the field lines themselves of the individual charges in the way I've spent all morning showing you. So I know that if I looked at that, those field lines are all pointing in radially. So at this point, there would be an electric field line associated with charge 1 radially going into that charge, and I could draw it from that point, since that's the point that I'm considering it for this problem. So I would call that E1. Likewise, for all the other two charges, the positive charges, again, it's a monopole and it's positive, so its charges radiate outwardly away from that charge. So at point P, there would be a field line originating from the center of charge 2 going through that point and pointing away from that charge like that. So I would call that E3 or E2. And similarly for E4, the same thing. It would be kind of along these lines. So that's kind of how I think about it. I just mentioned the test charge thing because I know your book is going to mention it, and I didn't want to not say something about it in class. But I don't really use the concept of a test charge in the way that I think about it. I do what I just showed you. I visualize the field associated with the charges. And because I don't need all of that, I'm not really concerned about the field particularly associated with that charge individually. I am and I am not. I want to know what its contribution is to a point. But when I think about its direction, I can just visualize the field lines radiating outward, radially away from that charge, and know that it must go through the point at which I'm considering consistent with the direction associated with its own individual field. And so at point P, then I have 4 vectors representing the fields of these charges at that point. And so now I'm back to vector analysis, right? I have to go back to that charge, set up a coordinate system, and basically do what I showed you last week, where we did it for a force using the force equation, but now we could just use the field equation that we just derived. So I have a set up an axis, right? Y and X, and now I have to go through and just figure out, start with that 5-step process. Determine the magnitude of the fields, determine their angles, the individual ones, and then find the components of those things, add those components, and then to find the components of the resultant, then use the component of the resultant to find the resultant. So I could then do that for a discrete charge distribution like the following, or I could have a continuous charge distribution. I could have a line of charge, a very thin line of positive charge, for example, in a region in space. And I want to figure out the field associated with that guy at some point P. All right, maybe I put, again, that's point P. I put a bunch of charges on a thin geometrical figure. I don't know, maybe it's a metal wire, and I've charged it positively. And I want to know the field at point P associated with that continuous charge distribution. Well, basically, I do the same thing that I did here, but with calculus. I have to break up it into what are the separate charges? Well, they become differential charge elements, DQs, not Qs. So I take that little element there, that DQ. If it's positive, I know that it's going to have a contribution at this point where it has an electric field that's pointing radially away from a line going right through that charge distribution, through that DQ. And so therefore, I would get a field that looks like um, well, this electric field here would be pointing radially away. So something like that. Now that I would call a differential field E, not a specific field, because now I have to go through and do that for each one of the differential elements and then add them up, and that will give me the field associated with that continuous. So again, we're back to considering what the equation for E looks like for a discrete charge distribution as opposed to a continuous charge distribution. This is continuous. And this would be considered discrete. So the form of the equations are the following. For I guess we'll just write all 3 of them down here. So the electric field of a single charge, I guess, would be defined as K sub B Q over R squared R hat. For a discrete system, whether it's two charges or more, we're going to have E is equal to K sub B times the summation of the Q sub i's over the R sub i's squared. And for a continuous charge distribution, that summation becomes an integral, Q becomes a dq. K sub B integral of dq over R squared R hat. Okay. So it's a single charge. Single discrete and continuous charge distributions. Ooh, okay. So one of the things that I've done to illustrate the point in the relationship between force and field is we go back to the problem we did last Wednesday, where I had a 3-charge distribution. So I've kind of gone over here at the break just because I'm having a slow lecture day. Somehow my brain is not following. I worked out this weekend. Maybe it's just because my body fatigues or something. I don't know, but I'm not. Sometimes that happens. I try to stay as consistent as I can, clear as I can, but nothing that really put this lecture down. Let's go back before we take a few minutes break here and set up the problem that we did last week. Now that problem, we had a 3-charge distribution like this, where I asked you to find the force on the charge in the center. So Y and X, and 1, 2, 3, 4. 1, 2, 3, 4. So something like that. And we had a positive charge at the center, which I think was 5 nanocoulombs. So we have a Q1 here. I think I made that guy positive. And then at 3, -3, we had another one. And that was also positive. That was charge 2. And here I think I had 2, 3.3.5, 1, 2, 3, and then 2. So here, and that was a negative charge. That was charge 3. So what I want to do right now is I want to find the field at the origin. Find the resultant field at the origin due to this distribution of 3 charges. That's how the problem would be, probably how it would look if you were asked formally. So determine the field the net field, or the net field E at the origin. Well, as I described over here, it's going to be you need to figure out the direction and magnitudes of the individual fields at the origin due to all the fields and charges around, and then do vector analysis. So again, using a test charge is one way of doing it, but I don't do that. I just think about what the fields look like of the individual charges and draw one field line from the point where I want to find the field consistent with what the individual fields look like for the charges. So for number 3, I know it's a negative charge. Negative field lines go into that charge. So I'm going to have a field line pointing from the origin toward that charge, like so. I'm going to have an E2 going in there. And here, the positive charge going away, I want to have a field line for charge 2 at the origin, pointing away from charge 2, directed from a point at the center of that charge, like so. All right, so that's going to be this is E2. Another dyslexic moment there. And this would be E3. Now, what about charge 1? Well, one of the main points we made is that charge 1 cannot contribute to the field at the point where it exists because it's 0 distance away from itself. So since I'm using the formula E equals KQ over R squared, the electric field at the origin associated with charge 1, if I considered it, it's 0 distance away, so it would be infinite. So you always get an answer of infinite if you did that, of infinity. It makes no sense, can't divide by 0. So basically, charge 1 does not contribute to the field at the point where it exists, which is the origin, i.e. the point that we're trying to find the net field. So we just have those 2 vectors, and we would have to do vector analysis associated with those 2 vectors. Now, we can get the magnitude, let's put down the information. So I told you that last week that Q1 was equal to 5.0 nanocoulombs. Q2 is equal to 6.0 nanocoulombs. And Q3 is equal to negative 3.0 nanocoulombs. So that's still the same information that we had last week. And the distances are the same. So this guy is 3.0, negative 3.0. This guy is 3.45 something, 465 dash 2.0. And those are in meters, we're assuming. Assume those in meters. So from that, we could get the angles because we have their coordinates now, so we can use the tangent. Just like we did last week, I'm just going to write that down. I'm not going to explain that again because we explained it before. We know that this angle theta 2, I'll call it, will be 45 degrees because inverse tangent of 3 over 3 is inverse tangent of 1, which is 45. So that's theta 2. And theta 3 is inverse tangent of 2 over 3.4, approximately 3.5. So that led to, I think, 30 degrees. Theta 3, that guy. So we can use those values that we had last week. Theta 2 is equal to 45 degrees exactly. Theta 3 approximately 30 degrees, 2/3. So you would be using this version, technically this version of electric field. Yeah, it's like 30 degrees, 29.99 something. All right, so let's take a break there and then we can make it a little bit of a working break. I can give you what time is it? 9:50. Yeah, let's take 10 minutes, maybe 10, maybe 15 at the most, where you can maybe start to work on this a little bit. But it's a break, so if we take minutes and come back and at least start a 5, make some effort to work on it if you will. I guess it's just you and I maybe going, I don't know what I'm talking about, but most people are watching this through video, then obviously that's kind of a moot point in terms of the break time. But let's take a few. Well, I'm back a little bit longer than 10 minutes, but hopefully you actually did start to work on this a little bit. If not, then let's get to it. Look at it now. Ooh. So, you basically do the exact same thing we did last week, except that you only have a summation of 2 charges here. So you look at the components of each, right? Like we can figure out the electric field associated with each charge by using the formulas that we just mentioned. So we got the angles here because of, approximately 30. I didn't write it down. But let's go ahead and get the fields themselves. Pretty quickly. So it was like 29.99, whatever. 99 and some change. So the electric field for 3, this guy, right, it's just going to be, it's due to, it's going to be K sub B, Q3 over R squared. For R squared is, that distance. So that's just going to be the Pythagorean theorem, square root of those guys. So let's number the equations 1, 2. So E3 is going to be equal to K sub B, and we decided to use 8.99, right? E to the 9th. And that's Newton's meter squared per coulomb squared. This guy here is 5. What did you say? 3 is negative, but I do the absolute value, right? So we don't have to worry about the sign there. That's going to be 3.0 e to to the -9, that's nanocoulomb, and then divided by the distance, but that distance is going to be 3.465 quantity squared plus 2 squared. And I don't have to, it's just that, right? Because it's squared, right? So it's Pythagorean theorem. The distance is the square root of that, but I need the square of the distance, so it's just that. So then if you work that out, you get E3 to be equal to yeah. Um, all right. So yeah, I got E3 to be 1.68. And the units are Newton per Coulomb, right? You can see it here. Coulomb cancels here, and this is meter squared. So that's going to cancel the meter squared here. So one version of where you can write uh, electric field units per electric field is Newton. I mean, it comes out of the definition, right? E is equal to F over Q. So that's obviously Newton. So that's 1.684 Newton per Coulomb. And I'm going to store that in the register. I store it in 0. We'll have to go back and use that. And E2 is going to be, again, K sub B, Q2 over R2 squared. This is R3 squared, R2 squared. So that's going to be 8.99 e to the 9th Newton meter squared per Coulomb squared times, was it 5? Q2 is 6 nanocoulombs. So 6.0 e to the -9, and then divided by like 3, so that's 9, right? It's 3 squared plus 3 squared meter squared. Yeah, so E2 is going to be equal to and then divided by 9. So that's like 4.99. 44. I'm just, keep don't truncate it, right? Keep those values in your calculator. So I'm going to store this in store in one. Okay. So we have those preliminary values here. Well, now I have to find the components and add them. So if you look at this problem, this guy's got two components. So we call it E2X. E2X. And that guy is E2Y. And also we have E3X and E3Y. E3X. E3Y. Right. So again, I'm going to kind of whip through this kind of fast, but because it's essentially the same vector analysis process that we did with force. So the electric field component is going to be the resultant of those two components. So I'll call it ER, for example. I'll drop my numbering. So 4, 5, 6. So I can say that ER X, is equal to basically, and I'm taking the signs from this guy. This is obviously positive because it's pointing in that direction. That guy's negative. So E3X minus E2X. But E3X is going to be equal to basically E3 times the cosine of theta 3, which is approximately, 29.99, whatever. In fact, I should, just so I don't make an error, I should put, it's not exactly 30. So I said 2 into 3.456 or 465, 465 divided by, inverse tangent. So I'm going to store that in the register 9. I can go back and get that. Okay, so if I were to write this guy out, ERX is going to be equal to E3 times the cosine of theta 3, and then minus E2X, which is E2 times the cosine of theta 2, where theta 2 and theta 3 are the reference angles. Yeah. And I already put in the numbers just so you can see it. So ERX is equal to space here 1.684, and again that's I'm using the save value, so it's not truncated, times cosine of I just say approximately 30, 29. well, whatever, 29.99 minus E2, which is going to be 4.99 times the cosine of 45. So you put that stuff in and do the math, and you're going to get something like x equal to, looks like it get like 0.064, something really small. I'm just going to do it again here just to make sure. So we call 0, so it's cosine of this guy, we call 0 times, and then we call 1. Forty-five cosine times minus, and adding those two things. Try that again. So we call 2. And 2 is definitely 45. That's times. That's going to be minus. And from this guy, I'm getting 9 cosine 3, which is 0.1. Plus. Well, I had something off in my notes. Because here, I'm getting minus 2.1. Minus 2.0722. I'm going to store this in. I'm going to store this in. I've got an emergency call coming in. I think I need to put this. Go back and get that. Let me just go ahead and put this in. Minus 2.07. So this is going to go into register 1, 2, which this is store 2. And then this is 2. Yeah, 1 and 2. Okay, just a quick second after that. So if you take a look at this scenario here, I'm just going to look at this E3y is going to be E3 times the sine of theta 3. E2y is E2 times the sine of theta 2, these components here. Again, we reviewed the geometry last week, so I'm just going to go through it. So E3 times sine of theta 3 plus E2 times the sine of theta 2, which is 45 degrees. So putting in those values, R, Y, then it's going to be equal to so E3 going to be 1.6. That's going to be recall, restore this, store it in 2. So recall 0 times 9, and then recall I'm getting different values than the values I have in my notes. I'm not sure what's going on here. Recall 0. So I get the right, this thing here, but this is wrong. Did I not divide by 18? What happened? 3 times 3 is 9. Oh, right, it's 2 off. Sorry, I did the thing in my head. I said 3 squared plus 3 squared was 9. I remember I divided by 9. It is 9 plus 9, so it's 18. So that should be divided by 2. That's what's wrong. So recall, what's that, 1? My bad. Recall 1 divided by 2. That is, still, is that? Just make sure. 8.99 into 9, enter 6E9 negative times 18 divided by. Well, no, it's 2.99. Well, yeah, 2.99. So that's what that should have been like. Yeah, so this is divided by 2. So I'm gonna have to go back and do this answer again. This is slightly off. This should have been divided by 18, not by 9. So we should get 2.994. And so this is going to be 2.994. And this is going to be a slightly different answer. So go ahead and finish that, if you will. I need to take a quick break, and I will be right back. All right, I'm back. Yeah, so when we put that new value in, it's going to change it slightly. And so let me recalculate this. It looks more like it. Yeah. So store that one in register or whatever I said. 2. So this is actually minus 0.65 and some change, 59, whatever. And I'm storing that in register 2. Yeah. All right, so making that adjustment with equation 11 here, I'm not going to put in the numbers. I'll let you do that. But if we like write them out on the board, however, let me make this a bit more clear. This is E R Y. So we can visualize the two components here, as I mentioned before, and I'm going to put in the right numbers. And so we have E3 1.684 times the cosine of approximately 30 degrees. So, or times the sine, excuse me, of 30 degrees. Same thing, it's square root of 2 over 2, which is no, sine of 30 degrees is approximately 0.5. So times the 1.6, so recall call 0. That's the first term. And the second term is the .99 times the cosine of theta 2, which was 45, or sine of theta 2. So that's the same thing. 2.707 times that's 2.1. Yeah. So you add those things together, you get about 2.96. Sure, I'll go ahead and put the numbers in. Maybe it should be better. Just so you have it in your notes and there's no confusion. So that's going to be 1 for E3 was 1.684 sine of approximately 30, 29.99 plus 2.99 times sine of 45. And then that gives us an E3, an ERY. This is going to be 13. ERY equals 2.96 newtons per coulomb. Cool. So now we have ERX, ERY. Note that ERX is negative, so this component here, E2X, is actually larger than E3X. And we could redraw that. We did the other day, with the force, but if we were to redraw it and to get a visual representation, we have something that looks a little bit like this. And also notice that the Y component is much, much larger than the X component. And so we qualitatively, it might, be something like this. In fact, it's it might look something more like this is EY, ERY, and something like this is ERX. So the resultant will have a pretty steep angle in the second quadrant, and we can figure out its magnitude. So that's ER. So to get the magnitude, we use the Pythagorean theorem, and to get the angle, we use the inverse tangent. So we can say that ER is going to be equal to the square root of minus 0.659 squared plus 2.96 quantity squared. So that the resultant magnitude of the resultant electric field at the origin is going to be equal to, I guess something like 3.03. That's my notes, so let's do it again. Where that. And then I brought that to recall 2. That. Add it. And take the square root. Yeah, 3.033. I guess I did 2 significant digits. Is that what I did? Yes. I should have taken out to 3 significant digits. That's what I put a 0 on it. So let's just do that. So I'll leave it like that, 3.33 newton per coulomb. And the angle is going to be inverse tangent of those guys. So, I didn't store that, did I? No, I did not. So I can store it now. So I'll store it in 3. This is stored in the 3rd register. Yeah. So now to get the angle, which again, the reference angle is this guy here for the resultant. That reference angle will be the tangent of theta r is equal to its opposite over adjacent. So it's going to be the y component over the x component, right? If you drop the perpendiculars and look at this right triangle here. Okay. Use a different color to highlight it. But these are the legs, that guy and that guy. So it'd be like, this is E R X, this is E R Y, and the hypotenuse is ER. Hopefully you can see that with the green. And and this is the angle between them. Right. So this tangent is going to be, or theta R is going to be equal to ER, the magnitude of ERY over the magnitude of ERX. So tangent of theta R is equal to, or theta R is equal to the inverse tangent of ERY over ERX. So that's going to be equal to the inverse tangent of well, right over here. We're going to get something like tangent of 1. And ERY is going to be, the 2.99, 2.96. And then that divided by the, take the absolute value, right? So 0.659. And ultimately, I get a reference angle of again. Yeah, 77. The same thing we got the other day with the force, 77.4 degrees. But really what I want to report is the angle relative to the positive x-axis. So what I need to report is this guy. So that's going to be 180 minus that guy. And so the angle that is the defined angle for this vector is at the 3 significant digits is going to be 103 degrees. So 102. And I use that symbol for angle 102.5, and that rounds to approximately 103 degrees. So the magnitude of the resultant vector is 3.3 newtons, and the angle is 103 degrees. Now, we can check the definition of the electric field with this, right? We said that the electric field is defined as, so let's keep the numbering going here, 19, and I guess I should erase this, so it's confusing, 20. Now 21, we're going to say that E is equal to F over Q in general, right? So that means that F must be equal to Q times E. So there was a charge number 1 here. And because we didn't take it into consideration here, because as we have learned this morning, we're trying to find the value of the field at that point where charge 1 exists. So it doesn't contribute to that field. Only the surrounding charges do. Okay, so now we know the field at point P. And that field, at the origin. And again, whether I have a charge there, that's the point that I made earlier in class this morning. This field exists whether there's a charge there or not, because that field at the point is not, there's no contribution to that field at that point to that charge. So I take it away, the field is still there, that value of this field here. And its direction is pointing 103 degrees. Now, I do have a charge there, though. So, according to this formula, if I know the value of the field at that point, I should be able to just multiply the charge that I placed there by the field at that point, and that will give me the force on that charge due to that field. But the thing I want to point out to you is that we already calculated that. We calculated it directly last week when we did Coulomb's law. So when I multiply the charge times the value of charge one, when I multiply the field that I just calculated at the origin times the value of charge one, I should actually get the answer that we calculated directly last week. So all we need to do is to verify that we know that charge one is equal to 5 nanocoulombs. I've erased it, but we had said that. So let's just do that to verify. Let's multiply Q1 times the value of ER to see that we get the force that we calculated directly last week on charge one. So F on charge one is going to be equal to Q1, which is 5 nanocoulombs. Well, I didn't store that. I need to do that. So 5.0 is 0 nanocoulombs times the field, the magnitude of the field, which is 3.03 newtons per coulomb. And obviously, newtons per coulomb times coulomb is going to give you newtons, which is what we need. So F1 then is equal to, let me get this stored here. I think I still have it in here. Nope, I'm going to have to calculate it again. So we're recalling 2, we'll square it, calling 3, square it, plus square root. Yeah. Now I'm going to store that in 4. Yeah. Store it in 4. So when I multiply those things, 3.3 times the 5 nanocoulombs, I get 1.5, basically rounds to 1.52 times 10 to the negative 8. 1.52 times 10 to the negative 8 newtons. And I do believe that is what we got last week. So you go back and look at when we calculated the force directly last week, and that was indeed what we got. Just verify it in the notes. Familiar? Make sure. So we have yeah, 1.52 times 10 to the negative 8 newtons, and it was at 103 degrees. So it shows you that this formula is valid. This formula is definitely a valid formula. Okay. Now I want to emphasize that. So this is kind of the basically the end of the formal presentation of everything associated with Coulomb's law, the field, the force, the relationship between the two. At this point, normally what I would do is recitation, just problems, and looking at different examples and applying them. So basically, this is the basis of this initial chapter, I guess. And it's, we in addition to looking at the properties of charge and static charge, we now have Coulomb's law. Now, one thing I want to remind you about, or make you aware of, technically Coulomb's law is this thing. It's a force law. F, equals KQ. And I'm going to write it in terms of the integral form. So K sub B, Q naught times K sub B integral of dq over r squared. And we have the definition of the electric field, which is this equation. Remember, I told you I teach concepts, not equations. So I like to always distinguish between the names of the concepts. So that's going to be F, this F over Q naught. So that if you put these two equations together, you get another equation, an analytical equation for electric field. So this is going to be basically K sub B, then times the integral of the dq over r squared, r hat. So in terms of verbal definitions, this is what I guess the official names of these concepts. This is the mathematical form of Coulomb's law. Coulomb's law or Coulomb's force law. Coulomb, I think it was a French physicist. Michael did something, whatever, Coulomb. And these things were empirically figured out, just kind of how I built them in class. People just experimented, saw forces, and empirical means by observation. So they just looked at them and came up with the properties in the equation. So Coulomb's law and force law. Coulomb's force law, electrostatic force law, Coulomb's electrostatic force law, all these different names is what it'll be known for. This thing, 3 equal signs always means a definition. So this is the definition of the electric field. So definition of E. And that was done by Michael Faraday. This thing I refer to, it doesn't really, technically it doesn't have a name. I refer to it as the analytical form of the E field. That's a very cumbersome name, right? Analytical form of the electric field, or analytical, the practical, pragmatic form of analytical. Um, However, most books and I guess conventional physics refers to this equation also as Coulomb's law. So it's a little bit confusing if you don't know what they're talking about. It means that it's the version of the electric field that was derived from Coulomb's law. But it, loosely speaking, when you're in a book, someone will say, use Coulomb's law to, maybe, or in a problem, use Coulomb's law to calculate the electric field of a charge distribution. Well, I'm just kind of pinching hairs or splitting hairs here. Technically, Coulomb's law is a force law, so how can you use it to find the electric field? It's a popular language or somewhat non-specific language associating the fact that this analytical form of the electrostatic field equation comes from Newton's law in the combination of the definition of the field. So don't let that confuse you, and just be aware of what they're referring to. In fact, if you ask in the way many physics books present it, this equation does have a name, and the name is Coulomb's law. But that's confusing to me. It always was, because you can't compare apples and oranges, right? This is force and this is field. They're not the same thing. So I'm just have a little caveat here, I guess, just to warn you of that conventional language, but also that I don't use that. When I refer to Coulomb's law, I'm always referring to this equation and never this equation. When I'm referring to this equation, I will say the analytical form of the electric field, just so to distinguish between that. So that's just a warning to let you know so you don't get confused when you start to, you know, read books or read your book or look online for other descriptions of this concept and that sort of thing. Okay. So I think I'm still in, maybe that's what's going on with me. I'm having a difficulty transitioning. I don't want to make the mistake I did last week. Last week, I think I taught to 12 o'clock, but our class ends at 11:30. I think I kind of realize what's going on right now. I'm
Okay.
still, go ahead. There we go.
No, I said okay. Oh, I understand.
Yeah, I think I'm still transitioning from the summer class. That's what I
Oh,
think was happening.
it was long.
Yeah, yeah, it was longer. And also my pacing was slower. Not
Oh,
slower, it was just more, it's just a different vibe, right? Because it's a
yeah.
6-hour class. So now I'm trying to get this material done in a certain amount of time, and I'm kind of off. I'm going a little bit slower, and I can't formulate my
Oh,
yeah. I think it just hit me. It's taking two weeks for me, a couple weeks for me to realize, but that's why I'm kind of off.
oh,
Because
this semester is barely the beginning, so it's understandable.
yeah, yeah, but I don't think I ever noticed that before.
Oh,
But I think what happens, I know why, because I normally teach the first summer session. And for the first time in, I don't know, maybe 6 or 7 years, I taught the second summer session. And
oh,
so I usually have a month and a half between that's between the fall session and what I do during the summer. And so I guess it's not as noticeable. I'm starting fresh, but I literally like only had like a week break between the second summer session and this one. And so I think I'm still in that mode, and it's kind of throwing me off a little bit, my rhythm off. So I guess I'll
professor.
take me another week or so to get on by. Yeah, but okay, we got 10 minutes. I want to use the class because we can get by on pretty easy. But basically, let's go take a look at the book.
Yeah.
I think I should.
The homework was a little bit hard, professor.
Say again.
I took all day trying to do the homework, was super hard. I'll do and then put the answers, they will still come out wrong.
So it may be that your answers were wrong, or it may be that Wiley Plus is a very critical grader. So for any answer and also I think you can see the answers after you submit the homework, right? Or at some point, I
Yeah.
set it up that, yeah, good. So whenever you get something wrong that was right, if it was like, let's say that the answer was 3.25 and you put 3.21. I mean, the thing takes off like 9/10 of a point. And I don't know any way to stop that. I've tried all the different iterations of policies on the work, and I think it's a coding error.
Oh,
So if you get something like that, write me an email and specifically spell out the homework, the name of the homework, and the specific problems that you want me to go in and check, and I'll go in and regrade those problems.
okay.
That's the only way I can rectify this situation with Wiley. It's
Okay.
pretty finicky, and it will grade you, wrong for little things like that. And
So
it's not, it's actually intermittent.
once you get one thing wrong, it says partial, something like partial
Partial
grading.
credit.
Yes.
Yeah, but what I'm saying is sometimes the partial credit is too harsh. So when you
Oh,
get, and you can only check that, I think, once you look at the answers. So when you
Oh,
get something where the answer is very close, like your answer is 3.21, and they give an answer of 3.20, okay, so that's a significant digit issue, which is important because you see, I'm pretty stringent and strict about keeping up with my significant digits, storing in the calculator and all that. So I'm modeling that. That is important. But in
okay.
a question like that, you should only get, I would have only taken off 1/10 or maybe 2/10 of a point. So you get 8 out of, if the question is worth 1 point, you might get 8/10 out of 1. What Wiley
Oh,
will do is, no matter if you don't have exactly what they say, it's going to
yeah.
take off 9/10 of a point. And that's
Yeah, I
just too
know
much.
that.
So for the problems where that happens, I can't fix it. I think it's a coding error.
Okay.
So you have to tell me, if you send me an email with the name of the homework and the numbers in which that happened, then I will go back and I can manually very quickly go through, if you tell me, and regrade it and give you back, 7 or 8 tenths of a point or whatever it is. Okay?
Okay. All right.
Okay.
Thank you, Professor.
Sure. That said, I do agree that it's rigorous. This is kind of a level up course, right?
Hmm.
Because I mean, they're all level up courses in a sense, especially if you hadn't had physics anymore. But we're definitely going to get into the thick of the calculus at this point. So what I'm going to do on Wednesday is I need to go into continuous charge distributions and show you how to handle that. And in fact, I keep saying I'm going to do this and I didn't do it. I may have to have some addendum lectures where I record them. Um, so basically, we have two standard lectures that we are going to go into the modules, but there's some kind of, like, if I work more examples, more class examples and things, I just don't have enough time in class to work as many as I would like. Um, so sometimes I will work them outside of class. I'll film it, but if you get a notice that there's a film going on outside of class time, that's probably what it is. And you're welcome to join in if you want, but I'll film that and then load those into the module so that you have those as reference. Otherwise, you can still go to the lectures that are already posted there, because a lot of those examples, that's why I posted the lectures for the short semester, because they're much longer, 6 hours. So I work sometimes more examples in those class periods. So you could always find them in there, but it's kind of cumbersome because you have to go through the whole lecture to find the examples. Usually that's the last couple of hours. But I think I'm just trying to, each semester I try to better the module for these classes. So what I'm doing this semester is I'm going to do these breakout sessions where I film them, extra problems, and put them in for the topics that we've been doing that week. So then you have them as addendums to those two main lectures for the week. So for something like that this week. And yeah, and that should help with the homeworks and help to reiterate problem solving technique and things like that. Okay. Oh, she's not there. Okay. Well, for those of you who watch the video, that's what's going to be happening. Um, I still have a few minutes. Let me go back and do a problem that, speaking of example problems, this is one that does not involve integration so much, but I want to go back and reiterate my problem solving technique with a problem like this problem. Really nice problem that illustrates that. And I know I did that early on in the semester, the first day, I think. But the thing I like about this problem is that it allows me to review the problem solving technique in the context of concepts that we are now studying this semester. Now, nobody's here right now, and I might go over a few minutes, but that's cool because I think I started about 8 or 10 minutes late. So I want to get I don't want to cheat you in this lecture. So yeah, we'll do a little bit of recitation right now, and we may go over a little bit after class. So this involves a discrete charge distribution. Again, two charges. but we're going to have these charges of like charge, and we're going to take these charges and put them on something called pith balls. They're kind of like very small cotton balls or mothballs, if you know those kind. Yeah, actually, a mothball would be a good example. A great example, because mothballs usually develop a little static electricity. You know, mothballs are my grandmother and my mother used to use them back in the day when you store clothes over the winter or whatever in drawers, or when you put them in chests and store them in the attic or something like that. You put these little balls in them that are supposed to keep moths out, and they're called mothballs. I don't see them much anymore, but these are kind of these old school things from the 50s. And yeah, and mothballs are kind of like these little pithy balls, almost like very kind of hard, wound up balls of wool, basically. And they put some sort of, I don't know, chemical or scent on them, and it keeps the moths away. But they're pithy, like pith balls, and so they, if you rub them on something, they'll pick up static electricity. So you have them in these drawers on clothes and things, and so they often do to gather static electricity. And they're pretty light, just a wound up ball of like wool, let's say, it's wound up into a solid ball. So let's say we take two balls like that and we charge it with some static electricity. We make them the same charge, like charge. So they are, and we put them on these strings, and we hope strings are the same length, so that, if they had no charge, they would just kind of exist together, right? Right next to one another. But if they're both charged with a positive charge, they're going to repel, and they're going to swing out, and they're going to repel such that they're at some angle relative to the vertical. And they'll come to static equilibrium at that point. We'll call this Q1 and Q2. So, and we would be able to measure the angle. So the given value, what's going to be known is we're going to know the angle at which they come to equilibrium relative to the vertical. We'll make it, and it's yeah. So we'll call this is theta, and so this is also theta, and we'll say that Q1 equals the value of Q2, which equals, I don't know. Actually, what am I looking for here? Because you could set the problem up various ways. The way I did it, two particles suspended at 35 degrees to the vertical by strings of equal length, L equals 0.35 meters. The two particles are of equal mass. However, Q1 is equal to 420 nanocoulombs, where Q2 is unknown. Oh, I set it up even more, a little bit. So they're not the same. I made them different charge. Well, that's good. That's a much more complex problem of unknown charge. So I think what I'm asking is determine the charge, determine Q2. Yeah, that's a little bit more difficult than making you could. All right, so let's do that. We have Q1 and Q2. Now it's interesting. You might first think to yourself, well, why would they, if the charges are different, why would they expand and have equal angle? Why would that symmetry be there? Well, it's because of Coulomb's law that it's proportional to the product of the charges. So just like we said before last week, even though these charges have different magnitudes, the repellent force associated with the electrostatic force between them is equal in magnitude on both charges. So therefore, it would cause it to expand or separate through the same angle. And that's a property of charge, property of Coulomb's law, property of the force law that we discussed last week. Okay, so let me write out the problem then so you can have it in your notes. And then I'm going to go through, and this kind of problem lends itself quite well to the problem solving technique, PPST. So I'll be pointing out those steps as we go through. So Q1, I think we gave it, I said it's 420. Write it up here, 420 nanocoulombs, 3 significant digits. And actually, only 2 significant digits, is it? I'm going to, well, sure, I'll leave it at nanocoulombs. Nanocoulomb, because I'm going to make the angle to 2 significant digits, or the length. So the angle, theta, is equal to 35.0 degrees. And then the length L, which is this guy, is equal to, that's where the 2 sig dig comes in, 0.35 meters. So 2 significant digits. We're going to, so this problem is the following. If we have, what did I say? 2 particles are suspended at 35 degrees. On strings of equal length, L equals 0.35 meters. The masses of the particles masses are equaling at m equals, I'm just going to make up something like, let's say 5 grams. So 5 grams would be something like 0.005 kilograms. So 0.0050. Yeah, we have 2 significant digits, don't we? So m is equal to, let's make it 15. So 0.0150 kilograms. That's 15 grams, yeah. If charge 1, if Q1 is equal to 420 nanocoulombs, what is Q2? Assuming static equilibrium of the system. Let me read that to make sure you have that correctly in your notes. 2 particles suspended at 35 degrees on strings of equal length. The masses of the particles are equal at m equals 0.0150 kilograms. If Q1 is equal to 420 nanocoulombs, what is Q2, assuming static equilibrium of the system? Okay, I think that's cool. I think that's cool. Yeah, so let's take a look. So there's a repulsion force, Q1 and Q2. So what we get is, we just go ahead and put that force right out. We've got this guy here. That's going to be FE. And directly in line, through that is the opposite repelling force, FE. That's what causes them to separate. But we also have a tension force on the object, a tension force due to the strain. So you might have remembered problems like that from last semester. So we got T, and it's symmetric, so we only really need to do one. But I'm going to put the force on this guy. Actually, I guess we do need to put the force on that one since that's the charge that we want to find. So that's where I'm going to place my origin. But just from the symmetry of the problem, we have all the same type forces, right? Those guys. And then gravity is also, it has a mass, right? So there's gravity acting on the object straight down. So mg. Same thing here. mg. So basically, I'm going to focus on charge 2 because that's the charge I don't know. So I have to go in and I have to place a coordinate system so that I can evaluate that problem. So my coordinate system, I would center my charge on that coordinate system, like so. Right. On charge 2. So then my first approach, so again, I'm kind of demonstrating the problem, right? This is step 1 of the problem solving technique. Step 2, explicit and implicit information. Well, explicit, I've got it all stated here. Just put it here, got the charge Q1, 35 degrees, 0.35 meters. I need to put the mass up there somewhere. The mass equals 0.0150 kilograms. So all that X is explicit information. Implicit information is that, since it has a mass, it has a weight. So there's a gravitational attraction on there. I don't need to place that anywhere. Weight is going to be mg of the particle. But yeah, and just kind of thinking about, what this situation is, and that it's in static equilibrium. So if it's in static equilibrium, I don't have any acceleration, right? There's no motion in either the X or the Y direction. This would be the diagram and the sketch. So this is the diagram, and I've simply superimposed the axis on top of that. So the sketch is this, sorry. So then I superimpose my axis on top of my particle. That's the diagram. And I've drawn in forces that represent, vectors that represent my forces. Tension force, the electrostatic force to the right, gravity down. I can see that the electrostatic force and weight are along the coordinate directions, but my tension force is at an angle. So let me come over here and draw a free body diagram to represent that. So FBD. I'm going to draw 2. 1, I'm just going to redraw the object like so. Well, I guess I only need 1 really. And putting in the vectors, so here's my mass, it's there in the center. Now I've got mg down. I've got Fe to the right. Like I said, they don't need to be resolved. But I've got the tension force at an angle, which does need to be resolved. Now, if this angle is theta, if you think of the x-axis as parallel to the vertical for my system, then alternate interior angles are the same. So if that's 35 degrees, that's 35 degrees. So I have the vertical angle here of 35 degrees. Right. So I can resolve my tension force. My tension force here is going to be T, and that sine, right, is the dropping down the vertical here. So T, so just because it's on the x-axis it depends on what angle you're using, whether it's sine or cosine. In this case, sine of 35, so be careful about that. And the y component here is actually T times the cosine of 35. So that would be my free body diagram. I have all of my forces resolved. Now, this is basically what you see here will be up through step 4 of the problem solving technique. Now, step 5 says list the actual concepts that apply. Okay, well, clearly if I have an electrostatic force on the object, the information that applies from the chapter that we're looking at now is Coulomb's law. Coulomb's law, so that's what we're going to apply directly. So Coulomb's law, okay. And the equation associated with Coulomb's law is F equals K sub B, Q1, Q2 over R squared. Now, we got different forms of Coulomb's law, but this is not a continuous charge distribution, so you wouldn't use the integral form. And in fact, it's a discrete charge distribution, but only a discrete charge of 2 charges. So I don't need the summation thing in there. It's just that force, is equal and opposite, and the value of the force, I would put in the Q, and evaluate, put it into the formula and evaluate it. Now, one thing to be careful about, that R, this is also implicit information. This R is the distance between the charges, and that's actually not something that's given. So that's something you're going to have to calculate. R is actually this distance right here. Now you can see we can figure that out in terms of the geometry, but technically it's an unknown. We'll get to that. The other thing that applies, I'm kind of hinting here, equilibrium, that hints of Newton's laws, right? Static equilibrium. So Newton's laws apply. And which one? Well, the third always applies. Kind of moot point when you're asking that. So when I ask that question, it's either the second or the third that I'm applying, the second law or the third law that I'm really referring to. And in this case, in both the x and y direction, I'm in static equilibrium. So it would be Newton's first law that applies. Newton's first law. And for both the x and y directions, those look like this. Net force in the x direction equals 0, and the net force in the y direction equals 0. So equations 1, 2, and 3. So that comprises step 5 of the problem-solving technique. Step 6. Those are the generalized or general equations. So let's look at the specific equations. In other words, let's apply those equations to this system. Well, yeah, that's now that we're getting to we're more intermediate students, physics students, right? I want you to be aware of the fact that there's one technical protocol. We're going to have several concepts from here on out, but basically Isaac Newton brought us into the modern age. So usually Newton's laws will always be applicable. So I think it's kind of a good form, a good rule of thumb when you're starting working a problem and you're going to be applying Newton's laws, that's probably the first thing to apply as a fundamental foundational basis of evaluating, even if you don't directly use Newton's laws, because there's other ways to do problems, as you know by now, conservation of energy and things like that. I just think it's a pretty standard rule when you apply a coordinate system to establish all of the possible forces on an object, and then just, maybe evaluate Newton's laws, relatively speaking, to that system, even if you might go some other route to solve the problem. In this case, we will need that directly, but I'm just saying in general. So let's apply Newton's laws in the X and Y direction. Let's just go ahead and do that. So in the X direction, I guess I can start here. So Newton's law, net force in the X direction. So yeah, so oh yeah, sure, whatever. So what force do I have in the X direction? I've got Fe to the right and T sine 35 to the left equals 0. So that's going to be Fe minus T sine of 35 equals 0. So to remind you, net force equals 0. So the left side is the sum of the forces, and it equals 0 is just there's no acceleration. So that's what that is. Okay, let's apply equation 3 for the y direction. So for the y direction, and let's do this like this. Because this might be a little bit confusing. Let's make this equation 2. So this is Fe and then comes down to here. And then I'll make this, yeah, so I was kind of debating. So then for the y direction, the net force in the y direction also equals 0. In the y direction, we have t cosine theta up, so that's positive. T cosine 35, and then minus mg equals 0. That's along this vertical direction here. Now, I can go ahead and stick. So here, basically, I have two unknowns. The two unknowns are T and Fe. Well, actually, three unknowns, right? The three unknowns are T, Fe, and the thing that I'm asking you for, which is Q2. So three unknowns, here's where you ask yourself, are you equally determined? Do you have three independent equations? Do you have the same number of equations as you do unknowns? Since I have three unknowns, I need three independent equations. And I have them. I have Coulomb's law. I have the sum of the forces in the X direction and the sum of the forces in the Y direction. So at this point, I know that my physics is done, and I can then start the mathematical manipulation to find the mathematical path to the problem. So that's always, if you look at step 6, those are the things that you check before you proceed to step 7, essentially. So this is what the 6 steps would look like prior to, yeah. Now, again, for those of you who have me new and didn't have me with 37, this is a new process maybe of doing this, but like you notice a couple things. I've never asked myself at this point in this process, what equation do I use? Right? I'm kind of breaking the habit of doing physics that way because it's really about the relationships with concepts. And so one of the things that makes physics a little challenging is that people have to change the paradigm in which they think. When you do a problem, the first thing that you should think is not what equation do I use, but when I'm trying to give you a process to go through, what information am I given? What is the sketch look like? What does the diagram look like? What concepts? Just that process, and it leads you to. Because when you get down here, even if you still didn't know how to do the problem, just continue following your technique. I've got 3 equations and 3 unknowns. So I basically need to solve those equations simultaneously to get rid of the unknowns. I'm going to have to go in 2 or 3, in this case, 2 levels deep. I go in on substitute to eliminate T, then I eliminate FE, and what's left is Q, or however, whatever unknown. And then once you have Q, I didn't ask you what the tension force is and what the force, the Coulomb force is, but now that you have Q, you could go back and find those other unknowns. So that's the process. So at this point, I'm gonna, the math is done. I'm in step 7, and step 7 sees solve it. So I also think it's important to just take a little bit of time to look at the equation to figure out the mathematical path that you're going to take before you start that process. And here it's pretty clear to me. I want that guy. I want Q2. So if I take equation 1 for FE and substitute it into equation 3, that's going to eliminate FE. So that unknown is out. Then I just have 2 unknowns left, T, tension, and Q2. Well, you can see that there's a tension here, there's a tension here. So if I then, maybe I could solve this equation for T, which I can, and then substitute that into, that resulting equation, then I'm done. I find my Q2. That eliminates all the unknowns, and I get it. So it seems like that's the route I can go, so that's what I'm going to do. So equation 1 into 3 yields K sub B, Q1, Q2 over R. Oh, also, sorry, actually R is an unknown as well. So I'm going to need a 4th equation, but that's pretty simple. We'll get to that. It comes from geometry. So there's 3 equations from physics and then 1 equation from geometry to solve everything. So I'll show you that in a minute. So minus, I'm putting it in here. So minus T times the sine of 35 equals 0. So let's handle the R right now because that's an unknown. Get rid of that. Now, it's easy though, because if you look at this triangle here, let's draw it right here. This is R over 2. This is theta, which I know, and this is L, which I know. So basically, tangent of theta or sine of theta is equal to R over 2 times L. So then R is equal to, we'll just write it out here. I can't do it in my head. I'm kind of tired or hungry or something. So sine of theta is equal to opposite over hypotenuse. So that's going to be R. So you can see my left hand. That's going to be R over 2 R over 2 divided by L. Opposite over hypotenuse. That's the same as R over 2L. Right? So that R then is equal to 2L times the sine of theta. And all of those quantities are known quantities, so that's what R is. So technically, actually, there are 4 equations. There's Coulomb's law, because there's four unknowns. Q, T, F, and R. F is Coulomb's law, the two equations from Newton's law, F, X, and Y direction, and the geometrical relationship of sine, cosine. So now I'm going to substitute 8 into 6, and that's going to eliminate R. And then we're on the down slope. So K sub B then, Q1 times Q2 over R, which is this thing, 2 times L times the sine of theta, minus T times the sine of theta equals 0. Okay, almost done. Still got two unknowns in this thing, Q2 and T. I've eliminated the two unknowns R and FE. So what I can do now is, so if I solve equation 5 for T, that's going to be T is equal to mg over cosine 35. I do that in a step here. I'm going to erase this. So from 5, we have equations, so it's going to be 10. From 5, we're going to have T is equal to mg divided by cosine of theta. So now if I substitute that into this guy, look at what I have. So 10 into 9, it's going to be K sub B, Q1 times Q2 over 2L sine theta equals T, which is mg, so not equals minus mg. Now that's going to be sine over cosine, so ultimately that's tangent, but I'll do it in 2 steps. Sine of theta, right, equals 0. So now that's it. That's essentially the answer, but I just have to do the algebra because the only unknown in that equation is Q2. So if I solve that equation for Q2, I have it, I'm good. So let's do that. I'm going to take this term on the other side and also put in the tangent thing there. So K sub B, Q1 times Q2 over 2L sine of theta is equal to mg times the tangent of theta. Taking that sine over. And then I just, multiply all that stuff out or cross, algebraically manipulate equation 12. Why does it keep doing that? And I'm almost done here. I guess I don't need that anymore. So Q2 then should be equal to so it's 13. So we're going to get Q2 equals, so over there I already have the mg tangent theta over 1. Write it like that. Then I have to multiply by 2L sine theta divided by basically K sub B times Q1. Yeah. So, oh, sorry, I messed up. This is R squared. Sorry about that, R squared. So when I put back this in, this whole thing has to be squared. Whew. It just translates through, right? It's not R, it's R squared. So all of this is going to be squared. Okay, sorry about that. So, yeah, but still, that's it. So I could just do some algebra here, which I will now. So, yeah, that's cool. So we're going to get, in the end, 14, you're going to get Q2 is equal to mg tangent theta, and then this is going to be 4 L squared sine squared theta, and then over K sub B Q1. I'm going to kind of clean that up a little bit. For Q2, I'm going to put all the constants out front. We're going to do equals 4 L squared mg, and I write this as sine squared theta tangent theta, and then all of this divided by K sub B times Q1. And that would be my final result. So that would be the solution. And if I wanted to know the answer, then I just put in all the values. So let's do that. Let's do that directly with my calculator, I think. So, yeah, what do we have here? So we have 4, enter L, which is 0.35 meters squared, times M. What did I say M was? I have forgotten. I've erased everything. I just made up M. I don't, what did I say M was? It was here and I erased it. Well, I guess I could just make it whatever I want at this point. Yeah. Oh, I remember this point. It was 15 grams. So M is equal to 0.015 kilogram, 15 grams. Okay. So 0.015 times 9.81 times K sub B is 8.99 divided by Q1 was 420 nanoampere, so 4 divided by, okay, times 35 times squared times, and then times tangent of 35. Okay, that seems reasonable. That's going to be is that 4.39? Well, I don't know. It is what it is. So 4.39 microcoulombs is what that charge would be. 4.39 microcoulombs. Actually 4.40 if you round it off. 4.40 microcoulombs equals Q2. So that's what I'm getting with those values. Oh. Yeah, well, once you have that, then you can go back and find those other things, right? You can get T, the tension and the strain. Well, I guess you don't really need that. You can just do it directly already. You don't need the charge to do that since you have English. Then you can go back and get the Coulomb force between the two, which is here. Yeah, okay. Well, it took about 35 minutes. Well, that's just, I'll work some more problems this week. Probably we'll continue with this on Wednesday. But I actually may put in a session an additional session this week that I record outside of class. And so just be working more problems. Okay. I think it's important. I know a lot of people are not used to doing physics, but just doing like the symbols and things. But again, I'm following the problem solving technique, so it's giving you some idea about how to go about setting up these problems and more efficient methodology associated with problem solving. Okay, that's all I got today. Oh, yeah, but that's it. Have a good day.